and Basil Brinde. Third day of our workshop, and the title of this workshop is Recent Trends in Metrical Fixed Point Theory and Application. This workshop started on 25th of November and this will last till 29th of November. Few announcements are also there. So the participating some professors and faculty members and students, research scholars, you please check your names, particularly the spellings, properly at any cost in the first half itself, that we are going to transfer the list of the attending participants for the certificate preparations. So that's the reason, because the certificates is supposed to type or print. So in such cases, your affiliation spelling, your name should match properly as per your desire. So kindly check those while you are signing your attendance today. And one of my colleague, Mr. C.P. Dhuri, Chandraprakash Dhuri, he is assigned for this work. So in case of any, you please tell him. By tomorrow morning, most probably you will get the first copies, means Xerox copies of your certificates. Once again, you verify your affiliation and names both. So once that is over, then very next moment it will go for the printing. So after the printing, it has to be signed by 3 members. That's the reason that it will take some time also. And since the registrar has to sign, so he is highly occupied, so he has to find the time to sign at least 50-60 certificates, means it's not so easy. So kindly cooperate us in that regard. So yesterday we had a very good and excellent session, and the last session was by Professor P. Veeramani, and you have gone through all the concepts, particularly with respect to the points when Tx is not equals to x, then what happened. And like in the first half, Professor Brande, he already discussed about some, I can say that some sort of prediction, means some pockets where fixed point lies and various maps lies, that he discussed very nicely. Tomorrow first half, since Professor Brande not available, so me and Professor Veeramani will conduct the sessions in the first half, and second half Professor Brande will come back. So let us invite our honorable speaker of this day. I think there is a slight modification in the title. Of course, the contents are more or less the continued part of yesterday, and that is this I think the second part he is going to take in the first one, right, Professor? So applied fixed points, Interial's self-adaptive algorithms solving split feasibility problems. Professor Brande, please.
Actually, the title is valid, but it will be the second one, so I decided to have some introductory matter. So this. Hello again. Ready? Have you charged your batteries for today's work? All right. I'm happy to be here. I really enjoy this activity. Once again, I would like to congratulate Professor Murthy for doing this job. Not easy at all for those who are or were involved in such kind of event, organizing such kind of event is not an easy job. Sometimes people from outside could imagine it's very easy. It's not. So once again, thank you for offering me the chance to speak together with Professor Veeramani and yourself in this course, very interesting course on recent trends in metrical fixed point theory and applications. By the way, all the time I wanted to make a step into the topological fixed point theory, but did not succeed. My first step into fixed point theory was on topological fixed point theory, because my bachelor and master degree thesis was on approximating fixed points for the Brouwer fixed point theorem. We know Brouwer fixed point theorem ensures just existence and the challenges to construct algorithms to find this fixed point. So now we are inside this metrical fixed point theory, and for today my plan is to speak about some applied fixed point iterative schemes, and I'll do on a very particular class of mappings, a very particular part. You'll have an idea of what is happening. So, Professor, sorry, I forgot. After the first session, I suggest you to stand in front of this building on the stairs and take a picture, okay? Okay, all together.
So,
not now.
We requested all the participants, what the professor said is we should have a group photography along with our speakers, okay, and participants. Okay?
Because
don't go to tea first and then tea with a little bit heavy.
Because it's a very impressive number of participants, so it should, even for the organizer to have this proof, there were many participants. So, this is actually a link what I spoke yesterday and what I'll speak in the second talk of today. I want to remind you these 4 classes of mappings I was speaking yesterday. We are in the same setting, a real Hilbert space, with the same notation, so we are concerned with these 4 important classes of non-expansive type mappings. At the end of my presentation, I'll show you a list of many non-expansive type topic for possible research. So, non-expansive, quasi-non-expansive, case-strictly pseudo-contractive and demi-contractive. They are really classes of mappings that are relevant in applications. These are very important. I'll just mention in my talk, but this class of mappings, as I said yesterday, is one of the largest class of non-expansive type mappings for which we can approximate the fixed point by an iterative scheme. So keep in mind this definition. So non-expansive, case-strictly pseudo-contractive. This class includes non-expansive. Demi-contractive includes the class of quasi-non-expansive. And there is also a relation between them. So, I have to confess that I discovered enriched mappings just looking for this diagram. There is no place where we will find this diagram except this paper I published exactly this year. So I was looking many years ago about finding the relationship between non-expansive, strictly pseudo-contractive, quasi-non-expansive, and demi-contractive. Just look back. These are the definitions. So, Non-expansive are included in K, strictly pseudo-contractive. All people knew this. This inclusion was known. So also this, this inclusion was also known. Quasi-non-expansive is included in demi-contractive, but I did not find the global relationship between these classes. So I've been interested. At that time, I didn't know that this class SPC is the enriched class of Ni. I didn't know then the DC, the class of demi-contractive mappings, is an enriched class of quasi-non-expansive. Because after looking a lot, contemplating these classes of mappings, I realized this concept of enriching mappings. So I mentioned yesterday that in this paper I discussed this mapping, T1, T2, T3, T4, T5, which ensure the relationship between these classes. So what does it mean, this T5? It's a mapping which is demi-contractive, is not quasi-non-expansive, is not strictly pseudo-contractive, is not non-expansive. One map. This one is quasi-non-expansive, hence it is also demi-contractive, but is not strictly pseudo-contractive, is not non-expansive, and so on. This one is a strictly pseudo-contractive map, which is not non-expansive. This one is a quasi-non-expansive mapping, which is also non-expansive, and this one is a map which is non-expansive and is not not quasi-non-expansive. So this diagram shows the position of these classes of mappings. There is a huge research work on this class of mappings. If you, I'll have some figures about the number of papers we can find in MathSciNet. Lot of papers in fixed and point theory of non-expansive mappings. Existence of fixed points, approximation of fixed points of non-expansive mappings, and mainly applications in image restoration, signal processing, data science, and so on. Lot of applications we'll find for this class of mappings, mainly. Also for strictly pseudo-contractive, many for QNE, for quasi-non-expansive mappings, and also many enough for demi-contractive mappings. Because I just mentioned these examples, I want to show you these three, the map 3, T3. So this is a map which is strictly pseudo-contractive, is not non-expansive, not quasi-non-expansive, and so on. So here is the proof. And to prove that it is not non-expansive, it's easier, I've shown yesterday, but to prove that it is strictly pseudo-contractive is not easy, but it's elementary. This is the proof. So we consider the definition of the strictly pseudo-contractiveness. We insert here our data. We are led to this inequality. We can denote xy by t. Because xy is in this interval, t will be in this interval, and then using this inequality and some derivatives, we have that f is this f is strictly decreasing, and so our function f is less than f of 1 over 4, which is 3 over 5. So this map is strictly pseudo-contractive with the constant 3 over 5. So this should be one example how to. So keep in mind, this is a case strictly pseudo-contractive. This is a map which is strictly pseudo-contractive, is not non-expansive, and is not quasi-contractive, and so on. So also I mentioned that any quasi-non-expansive map is included in the class of demi-contractive, but we should prove that this inclusion is strict. So this is an example. Also not easy to construct. By the way, I've sent this book by Madalina Păcurar. This is extremely nice book because she succeeded to find an algorithm to construct examples. Very nice. So just what you ask about the relationship between contractive mappings, she succeeded to find a way, a method, a very nice method to construct examples. To construct examples is not easy. Sometimes we are working more on an example than on the proof. So sometimes we do the proof, we want an example, and we should always provide an example. This is the T5 map. I go back to show you this one. It's a map which is the most general from these mappings, so it's demi-contractive and does not belong to any of the other classes of mappings. And it is very similar to the examples you will find for contractions. It's very similar, but it's a more general class, more general mapping. So it has a unique fixed point that is reminding us the concept of Picard iteration, Picard operator, sorry, when we had, where are, huh? Here, sorry. I was looking for them here. So we remember that this was the definition of a Picard operator. Fixed of T is an X star, let's say, and B Tn of X converges to X star as n tends to infinity for any in X. This is Picard. Okay, here we have this first condition, but this does not work. So this conclusion does not work because we'll see we need Krasnoselski iterative scheme to approximate. And the aim is to show this map is not demi-contractive, is demi-contractive, sorry, and is not quasi-non-expansive. And also the proof needs some computations to discuss the first case. X is in 0, 1. And because we have this inequality to prove y is a fixed point of t, we have a unique fixed point 7 over 8, so our inequality will become this inequality, and it holds. This is easy to see, but in that case we have t 5 of x minus y is 0 for all x in 0, 1. So this is true for any k greater than 0. So the second case, just x equal 1, it's requiring separate treatment. So we have this quantity, and we see that this leads to such an inequalities. Hence, T5, sorry, is 2/3 demi-contractive. To show that it is not quasi-non-expansive, we have this example. We take x1 and y star here should be y star. Usually I denote y, but here I don't know why I have y star. So we get this contradiction. This means that our map is not quasi-non-expansive. Hence, we have for sure the strict inclusion of quasi-non-expansive mappings in the class of demi-contractive mappings. I had in this, sorry, here is T2, and here is T1. I forgot to change. These are the examples I mentioned in my diagram, T3, and was T4 and T5 and T6. This T6, it's also interesting to consider. It is, again, demi-contractive, is not quasi-non-expansive, is not strictly pseudo-contractive, is not non-expansive, also to support our diagram. So this was also the example of yesterday with the start from non-expansive mappings and quasi-non-expansive mappings and enriched. So, as I told you yesterday, I started from non-expansive mappings and I constructed this class of enriched non-expansive mappings. This was the first example of a map which is enriched non-expansive, is not non-expansive, is not quasi-non-expansive. And of course the proof is in the same lines I had previously. So the problem was, after I introduced this class, and for any similar situation, the question is this class of enriched non-expansive mapping a relevant extension of non-expansive mappings? If yes, we should relate this new class, because it is a new class of mappings. It is distinct of non-expansive, it is distinct of quasi-non-expansive. We should relate to the other classes of non-expansive type mapping. So this was the point. We did it, and we realized the following facts. Here, one more step. Look, this is our class of mappings, enriched non-expansive. We are in a Hilbert space. Here, the green should be the class of contractions. Very small, very small. It has many applications, but with respect to the other classes of mappings, it is rather small because it requires the mapping continuous. Also, non-expansive mappings are continuous, but enriched non-expansive, but quasi-non-expansive are not more continuous mappings. And what is important, in this class, green C, Picard iteration converges. So we can use this iteration scheme to approximate fixed points. But if you go outside, as I said, in the class of non-expansive mappings, then Picard iteration does not converge. And we have this example. Yesterday it was 1 minus x, but it's the same thing. So for any x0 which is different of 1, 2 minus x equal, yes, different of 1, we have an oscillatory sequence, so Picard iteration does not converge, while Krasnoselski-Mann iteration, as it was proved, converges for any lambda in this class and also in the class of enriched non-expansive. This was the example for enriched non-expansive. So Picard iteration again is not convergent for any x0 different of 1 of the fixed point, but Krasnoselski-Mann iteration, which is obtained by replacing the original operator T by its averaged operator T lambda, converges for any lambda in 0, 1. And I have here some numerical data about the Krasnoselski iteration scheme. Krasnoselski-Mann are saying people for different values of lambda. This is a very interesting problem, and I'll speak in my last lecture about error analysis of fixed point iteration. You can see the scheme is this one. So I started with n x0. So you can see we started with this first approximation x0 1.95 to be far away of 1, and you can see that for the values of lambda very close to 1, what happened when lambda is 1? What becomes this iteration? So let's say no 1, but tends to 1. Then our scheme will become exactly the Picard iteration, which does not converge. So this shows that when we approach 1, we enter the zone, the area where the Picard iteration does not converge, and the influence is that it converges very slow. We need 57 iterations for lambda 8/9. For lambda 4/5 is this number, 3/4 is this number, and you can see the fastest, at least in that case, for this starting point. It doesn't matter. This difference is not essential. Is for lambda 1/2. So in that case, our iteration is this one. And no, please be very careful. This was the form Krasnoselski used. Extraordinary. Average. So he did exactly the best position for lambda, the average. So the average improves the extreme, the two members of this average. Very, very nice. He was very inspired to do this. When we have a different starting point, you can see here something interesting, because when lambda is 1/3, then we'll have the solution after one iteration. But the others behave exactly in the same manner. So we start from 1/5. We are here. Our so it's here, and when we start from here, So we have this situation, and we started from here, from 2, and very close from here. So we had 3 initial points. Practically, the initial value is not significant except for this